Page 11 of functions. First it says, give an example of a linear function. A linear function is the famous y equals mx plus b or plus c, which, with numbers looks like y equals 2x plus 1, something like that. It also has the variations of horizontal line and vertical line. A horizontal line looks like y equals 7. Vertical line looks like x equals 3. Okay, so these are the three common formats of lines that you might see for a linear function. Okay, instead of y, you might see the notation f of x, right? F of x. Give an example of a rational function. A rational function looks kind of like a linear function, except for it's got a numerator and a denominator. So, for example, you might have a numerator that's ax plus b, and a new denominator that's cx plus d. And when I say ax plus b or cx plus d, what I mean is the a, b, and the c and d are just numbers. I'm just saying they could be any number. So maybe it's more clear if I actually put numbers in there. Like I'm going to put 2x plus 3, and on the bottom I'm going to put 7x plus 5. See how that works? Okay, I just filled in a, b, c, d with different numbers. The a, b, and c, d are not really variables. They're constants. They're like unknown number values. They're not variables like x and y, where x and y can vary from negative infinity to infinity, and that's how we create graphs. A little bit different. Describe in your own words what is an asymptote. There's two kinds of asymptotes we're going to talk about here, a horizontal asymptote and a vertical asymptote. So horizontal asymptote is the y value that a function approaches if I go very far to the left or to the right. A vertical asymptote, on the other hand, means that when you're approaching a certain x value, the function is suddenly going to go way up or way down. Okay? So if I was going to draw that, like if the function is like going like this, and then I go very far to the right, all of a sudden it's going to approach a certain value, and that dotted line that it approaches is an asymptote. If the same thing happens going to the left, then that's also an asymptote, right? A vertical asymptote is kind of the opposite. Let's say this is a certain value of x that when the function approaches that value of x, instead of behaving normally, all of a sudden it shoots way up or shoots way down, and that's a vertical asymptote. Okay, so basically it's a dotted line, an imaginary line, that the function approaches either going vertically or horizontally. Basically, when you make a rational function, which we just drew here, we are going to have vertical and horizontal asymptotes. We're going to see how that works. A reciprocal function is kind of the way it sounds. A reciprocal means like 1 over quantity, and a reciprocal function basically is 1 over x, or like 3 over x, or anything over x. Okay? So that's a reciprocal function. For a rectangular hyperbola, what is the value of f of x at x equals 0? Guess what? A rectangular hyperbola is the graph of this function, the reciprocal function. So if I graph that, basically what I'm going to get is something that looks kind of like this. And really the x-axis and the y-axis are going to be horizontal and vertical asymptotes in this case. I'm going to draw those with yellow lines. Okay. So what is the value of the function 1 over x at x equals 0? That's going to be 1 over 0. 1 over 0 is not 0. 1 over 0 is actually a huge number. If you divide 1 by a very small number, you're going to get a huge number, right? It turns out if you divide by 1 by 0, you get an infinitely large number, which is infinity. So at x equals 0, f of x does not exist, actually. It's an asymptote. Okay, so at x equals 0, that's this point right here, the function is not, doesn't have a value. What is the value of f of x when x equals positive 0.001? Okay. So if I want to find that out, all I need to do is put it into x here. So I'm going to do y equals 1 over 0.001. And that gives me a value of 1,000, I think. Positive 1,000. And what if I put in the value negative 0.001? What value am I going to get out then? I'm going to get negative 1,000. Oops. So now you can kind of see why the rectangular hyperbola function gives you like a very large number when you approach the vertical line in the middle from the right, right? If I put positive 0.001 in, which is very close to the line on the right side, I'm going to get a very big number like positive 1,000, right? And on the other hand, if I approach it from the left side and I put in a number like negative 0.001, which is just on the left side of the axis, I'm going to get a really big negative number like negative 1,000. Okay? So those are the two y coordinates when I put in two very close points, positive 0.001 and negative 0.001. They gave me two very different y coordinates, positive 1,000 and negative 1,000, and then you get this hyperbola shape. Explain why we cannot simply ask for the value of f of x when x approaches 0 for a rectangular hyperbola. Okay, so if you just put 0 into the equation 1 over x, we get 1 over 0, and that's basically an undefined number, because if we divide by 0, we don't know exactly what's going to happen. In this case, it turns out to go to positive infinity or maybe negative infinity, depending on which way you approach it, right? If you approach it from the right side, it looks like it goes to positive infinity. If you approach it from the left side, it looks like it goes to negative infinity. So moving down, how does a sign diagram help you find the vertical asymptote of a function? Okay, if you make a sign diagram for the function 1 over x, for example, you are going to find out that there are no zeros, but there is a value which makes the thing turn into an asymptote, which is x equals 0. If I put in x equals 0, it's going to be a vertical asymptote at that point. So I'm going to mark 0 here. I'm going to make a vertical asymptote at that point on the sign diagram. So basically, whenever you have the vertical asymptote on the sign diagram, it also is the vertical asymptote on the graph of the function. Okay, so I'm also going to have a vertical asymptote at x equals 0 on the graph of the function. What values of x would you put into the function f of x to find a horizontal asymptote? So basically, to find a horizontal asymptote, what you want to know is what happens when x goes really to the right or really to the left. And going really to the right means that basically you're putting a really big positive number in. Going really to the left is putting a big negative number in. So the values that I would put into x to find the horizontal asymptote is I would put like a positive big number, and I would also put a negative big number. By putting each one of those into the function 1 over x, I can find out what the y value converges to. Okay? So we're going to see that work in the next problem. We're going to start with this function here, which is 3 over x minus 2. Basically, this notation here basically means f of x equals 3 over x minus 2, right? Let me draw that horizontally here. Okay. First it says determine, they're going to ask us for a bunch of things which are going to help us graph this function. Okay, there's several things we can do to find strategic points instead of just making an XY table and putting in a bunch of numbers for x. Although this is a legitimate method also, there's a more sophisticated method which is finding the asymptotes, finding intercepts, looking at the behavior as it approaches the asymptotes, etc. Okay, so we're going to do that approach. Okay, so right now we're going to look at the equations of the asymptotes. So asymptotes, we know, can be found in the horizontal direction and the vertical direction. Vertical asymptotes are found because in the denominator of a fraction, sometimes you end up with 0, And when you end up with 0 in the denominator of fraction, that makes the function itself go to infinity or negative infinity, and then you're going to have a vertical asymptote. So let's look at this case. In this case, we have in the denominator x minus 2. For some values of x minus 2 becomes 0, and then we would have 3 over 0, which would be infinity. Okay? So x minus 2, the value that we could put into x that would make x minus 2 go to 0 happens to be x equals 2. So if we put 2 there, the denominator is going to be 0. And then we're going to have 3 over 0, which is positive infinity, right? Which would be a reason to say that there's an asymptote here, vertical asymptote. Okay, so we know that the vertical asymptote is x equals 2. And this is just like when you write the axis of symmetry equation. You do need to write x equals 2 because vertical asymptote is a line, and the equation for a line is x equals 2. It's not VA equals 2, for example. Okay? What about a horizontal asymptote? Is there a horizontal asymptote here? Well, let's see. Remember, we just said that the way you would find a horizontal asymptote is if you would put a positive big number in the equation and you would put a negative big number in the equation, and you would see what number that function approaches. So we have the function 3 over x minus 2, and the first thing we're going to do is we're going to put a positive big number in for x. So we're going to put 3, and we're going to put positive big number for x equals positive big number. And we're going to put in that here. So let's put like a million. A million minus 2 in the denominator and 3 on top. So what does that give us? It gives us like 0.000003, right? A really small number. So we'll say small positive number. Okay. And then we're going to do the same thing with a negative big number. So we're going to start with 3 over x minus 2. We're going to substitute in a negative big number, and that's going to give us 3 over negative a million minus 2, which gives us 3 over negative a million and 2, which is negative small number, right? So it's small negative number. Okay, and when I say a small negative number, I mean really small, 0.000001. Okay, basically what's happening, and you can see this if you put in even bigger numbers, the bigger number you put into the denominator of 3 over x minus 2, you're going to get an even smaller number for the result of 3 over x minus 2. So you're going to get the farther out you go, the smaller the number becomes, and then basically when you go out an infinite distance, you're going to get a 0. So basically here, what we're saying is that the horizontal asymptote is y equals 0. Okay? And let's draw the asymptotes with a blue pen. So we're going to draw a vertical asymptote at x equals 2. And we're going to draw a horizontal asymptote at y equals 0. And that's what they look like. Okay? Then it says to state the domain and range. Okay. Once you've done the vertical and the horizontal asymptotes, it's kind of easy to do the domain and the range, because the domain and the range are the valid x and y values, and the vertical asymptote and the horizontal asymptote are kind of the invalid vertical and horizontal values. So, for example, if I say that the vertical asymptote is x equals 2, then the domain would be x is not equal to 2, right? If I said that the horizontal asymptote is y equals 0, I would say that the range, this is the domain, the range is going to be y is not equal to 0. Okay, so once you say the horizontal asymptote and the vertical asymptote, you already kind of know the answer to domain and range, because they're opposites of each other. Okay? Alright, let's look at what's next. Find the axes intercepts. Okay, we've done this before, right? With parabolas. We can find the axes intercepts by putting in strategic values in for x and y. Okay? So, for example, if we want to find the axes intercept, the y-intercept, The way we find the y-intercept is we put the x value in for 0. So let's do 3x minus 2. We're going to substitute in x equals 0, and that's going to give us the y-intercept. So the y-intercept is equal to 3 over 0 minus 2, which is 3 over negative 2, okay, which is also equal to negative 1.5. So that's the y-intercept. What about the x-intercept? So the x-intercept is just the opposite. You take y equals 3 over x minus 2, and we're going to substitute in y equals 0, and that's going to give us the x-intercept. It's a little bit more tricky because we're going to have to solve for it with algebra. Okay, so we have that, okay, and then if I multiply both sides by x minus 2, I'm just going to get 0 equals 3, and that would be just nonsense. So I have to suspect there's something wrong here. Basically, if you look at this, what value of x could I put in there to make this true? Well, I would have to have 3 over a huge number to make it equal close to 0, right? So I would have to put in like x equals a billion million, but probably it would be better put x equals infinity. Oh, x equals infinity, so that makes it sound like the x-intercept doesn't exist. And that's true. If you look at it, the x-intercept would be where the hyperbola crosses the x-axis. But wait a second, it's an asymptote, so it can't cross the x-axis. So that's exactly why there's no x-intercept. So the answer here is that there is no x-intercept, okay? All right, discuss the behavior of the function as it approaches its asymptotes, and sketch the graph of the function. We can do those both at the same time. So, for example, we already know that if we put in a big positive number in for the function y equals 3 over x minus 2, we get a small positive number. So that means as we go out to the right, we are going to have a small positive number. We're going to approach the asymptote y equals 0 from the top, okay? So we would say as x approaches infinity, positive infinity, y approaches 0 from the top. What about when x approaches negative infinity? When x approaches negative infinity, a negative big number, we get a small negative number. So we know that when we go to the left, we're going from the bottom. We're approaching a small negative number. So as x approaches negative infinity, y approaches 0 from the bottom. So do you see how the positive and negative sign, we're writing it after the 0? That basically is a new notation. Instead of saying negative 0 or positive 0, which makes no sense, we're saying, oh, it's a little bit above the 0 or a little bit below the 0. Okay? So we've figured out what it kind of looks like on the horizontal asymptote. What does it look like on the vertical asymptote? Let's remember that we figured out that the vertical asymptote is actually at x equals 2. So when we approach the value x equals 2 is when we start having weird behavior. So let's say as x approaches positive 2 from the right, and as x approaches 2 from the left, positive 2 from the left would be 2 and then negative superscript. Let's figure out what happens to y, okay? And we can tell by putting a number that is slightly above 2 and slightly below 2 in for the function. So let's do y equals 3 over x minus 2, and what we're going to plug in first is a number that is slightly more than 2. So we'll say x is equal to 2.0001. That's going to give us a y value of 3 divided by 2.0001 minus 2, which would be 0.0001, which is equal to 30000, which is 30,000, a huge positive number, right? So a big positive number, right? Let's see what happens when we put into 3 over x minus 2 a number that is slightly smaller than 2. So we're going to put x equals 1.9999. Then we'll have y equals 3 divided by, 1.9999 minus 2, which would be a negative 0.0001. 3 divided by negative 0.0001 is equal to 3,0,0,0,0. It's negative 30,000. So it's a big negative number, right? So if we're going to graph that, we know that if we approach 2 from the right, like 2.0001, we're going to get a big positive number, so it looks like that. If we're going to approach the value of 2 from the left, like 1.9999, then we're going to get a big negative number, which means it'll look kind of like that. Okay, so that's how we get those numbers, and we've sketched the graph, and I'll just connect them here, okay? And this isn't a really good graph, but it does show you well what happens when you get close to the asymptotes. And, I could take advantage of the fact that we know that the y-intercept is negative 1.5, right? I could draw that part more accurately. So let's say negative 1.5 is right here, right? Then here I know that it approaches the asymptote, and here I know it approaches the asymptote. Okay, so that's a little bit better. All right, and that's all you need to do. Oh, I did forget to note, so as x approaches 2 from the right, I get a positive big number, also known as positive infinity. As I approach 2 from the left, I get a negative big number, also known as negative infinity. So that's how you would note that. Just one more note. The way you annotate that is when x approaches 2 from the right side, I would look here, that's 2.0001. What does that look like? It's 3 divided by 0.0001, which is a positive big number, also known as positive infinity. When you approach 2 from the left, like at x equals 1.9999, what do you get? You get 3 over negative 0.0001, which is equal to negative 30,000, which is a negative big number, also known as negative infinity. So that's how you note that.